Welcome to the School of Batman, a podcast where we ask academics to help Batman fight crime using their research. I'm your host, Chris George, amateur scientist and professional Batman enthusiast. And in today's episode, we'll be discussing the asteroid from Krypton. We're pleased to be joined by Chris Jackson, who has a BSc in Geology from the University of Manchester, and also a PhD in Tectonics from the University of Manchester. Chris, we'd like to start the podcast with a bit of background on yourself, your academic journey, what inspired your choices, what were your childhood interests, and a few details about your research. So tell us about yourself.
Yeah, so I was born in the East Midlands in a city called Derby, and I spent most of my childhood days playing sport. So just running and jumping and running and occasionally going to school, then running and jumping a bit more. So I was always kind of very, very active and spending a lot of time outdoors as well, so a lot of caravanning and a lot of camping as well, which may explain why when I had the choice of degree course at university, I chose to do geology. I guess there's a stereotype of geologists kind of wearing Gore-Tex and waterproofs and romping around in the hills and always loving being outdoors and climbing. And you know, that's not true, but in my case, there were some of those elements were certainly true. So I ended up going to Manchester to study earth sciences. And
your PhD in Tectonics, could you tell us a little bit about what you were doing there?
Yeah, so I was always interested in... I was never particularly good at anything I did at university, and I was a little bit good at quite a few things. So this study of plate tectonics and sedimentation was perfect for me because it meant that I got to go and study, you know, several different aspects of earth sciences during the course of my PhD. And also, I loved doing field work and being outdoors. So my PhD was based in Egypt in the Sinai Desert. So we spent several months out there collecting rocks and measuring rocks and sort of smashing rocks up and carrying the rocks back to Manchester. So it was ideal. So yeah, it was a really enjoyable experience, but very challenging for me because I wasn't the intellectually strongest PhD student, perhaps.
So what kind of sciences? You said there was a mix of different sciences. What kind of sciences are involved with tectonics or with geology in general? What kind of things do you need to be aware of? Is it a collaborative form, or is it the kind of thing where you actually need to know that information yourself?
No, so earth sciences draws on physics, chemistry, biology, maths. It draws on all of those things to varying degrees in the different kind of sub-disciplines of earth sciences. What's really great nowadays, I would say, is that you can almost get away without being expert in any one of those because we're increasingly asked and increasingly inclined to do collaborative multidisciplinary research. So reaching out to physicists or biologists or chemists to tackle something which we can't do with our kind of more fundamental knowledge of some sedimentation processes. That's what's really exciting about it at the moment. So you don't need to kind of do this research in a siloed manner anymore.
And how would that kind of thing work in reality, and why has there been a change? Has that change occurred since you've been involved, or has that change been occurred over a matter of decades, say?
I think that sort of integrative research started before I started my PhD. Why has it happened? That might be because some of the questions we're trying to answer in earth sciences are very, very complicated. And so as you get down from some of the fundamentals and you start getting into some of the real details of any particular area, simply collecting rocks and smashing rocks up and carrying rocks around isn't enough. You need to be quantitative. You need to look at the chemistry of the rocks. You need to look at how life has evolved on Earth and what that tells us about climate and climate solid Earth interaction. So I think the questions we're trying to answer require us to all get together more than it previously did.
What's driven the complications in those questions? What is it a case of all of the kind of more fundamental work has now been done, or is it a case of more interaction with industry, or why are you trying to answer more complicated questions now?
I think one thing that certainly in the area that I work, some of the tools and the data types we use have got better. So you see more. And when you see more, you realise that you don't understand things in the same way as you did before. So some of it's data-driven, that we just have better ways of processing data. We have more computers, we have better sensors, we have, better kit for chemical analysis. So we see more details there. There's a natural, inquiry that humans have. So, old data, new minds, new ideas. So you can go back to something with these kind of integrated teams and try and pull more out of it. Obviously, there's a technological demand, or there's an industrial demand by companies in the extractive industries where I do quite a bit of research. It's harder to find hydrocarbons, so you need to think a bit deeper and use different techniques to try and locate them. So I think there's lots of different forces pulling at that desire to answer more tricky questions.
So is it fair to say that geologists of old simply wouldn't have known these questions to ask, or have these questions existed since kind of time immemorial and the tools weren't available to do it?
I think it's probably the latter. I think people were probably thinking of some of these the big unanswered questions of our time, but they knew that it was at that moment impractical or impossible or too expensive to do it. So I have no reason to believe that we're more, we think any harder now, or we're more interested in the earth, so we're asking different questions now than people were decades, hundreds of years ago. I mean, some of the greatest discoveries were done and the most fundamental things were done, hundreds of years ago. And
you mentioned hydrocarbons there. Could you tell us what hydrocarbons are?
So yeah, hydrocarbons would be, to kind of translate, that's oil and gas are the two main hydrocarbon types. So, which are formed in the earth. For the large volumes of them, they're formed in the earth, and that's where we have to explore for them and produce them from, is beneath our feet.
And you mentioned collaboration with industry. Is that something that's been long working hand in hand with geologists? Is collaboration with industry been a financial or even intellectual driving force, or is that something that's become increasingly prevalent as time goes on?
It's a very good question. I'm not sure. I guess in the past there was kind of never the twain shall meet. There were very separate entities, and there was an industrial driver, and maybe the academics at that time perhaps were less savvy at communicating how fundamental research could help the applied industries. The whole ivory tower sort of phenomenon that, we think great deep thoughts and that's enough. But now it's completely different, where there's a whole generation of scientists who are very, very savvy, because they realise, and industrial people as well, who realise that those fundamentals, if you kind of extract the right bits out of them, they can be really useful in terms of, bottom line, increasing revenue. So certainly my generation have grown up being very well aware of that. There's PhDs funded by industry, there's research projects funded by industry, there's industrial sabbaticals, there's lots of ways that industry and academia work better together now.
I think as a non-academic myself, it's quite difficult to imagine how that partnership might work. So are you tasked with an explicit applied outcome, and then theoretical finds are bonuses, or how does that actually kind of work in practice?
Yeah, sometimes you're asked a very specific question, and it's something, sometimes it's, in my case, it's something that the kind of energy company doesn't have time to do, right? So it's going to take 3 years of effort, or combined, 10 years of effort to kind of get anywhere with this. So they don't have the time to do this because their kind of staff are working elsewhere. So, that job will go out to, or that research will go to an academic to do. And so you have a bit more time of like deep thinking and coming up, and a few more false starts. And sometimes it's as simple as the equipment resides in academia and not in industry. So some of the analytical work can only be done by companies external to the main, the main energy company in my case. So yeah, I think there's sometimes very specific tasks. Sometimes you get bonus balls, there's you do a project and something very blue skies arises from it, and that's great for you, and maybe the industry aren't that concerned, but you can still use that going forward. And sometimes you can go to an industry partner and say, like, I have this rather blue skies thing I'm interested in, but we think there's a few kind of things that could come out which are of interest to you, and some of the bolder companies or the right people in those companies will fund that research.
Great, well, thanks very much. Now it's time to move on to your story. So for your story, we ask our guests to choose which Batman actor they would like to represent their Batman in their story. So do you have a choice for your story?
Yes, easy, Michael Keaton.
A great choice. Could you tell us a little bit about why you liked Michael Keaton?
Because when he was chosen, it was around the time I was starting to watch movies which were given a rating of 12, I think. So it was like, so he was a very visible actor to me. And also, he didn't make a lot of sense as a choice, did he? No, I agree. There was a lot of controversy, I think, when he came out, but I agree, he absolutely nailed it. Yeah, he wasn't the kind of dashing, handsome, suave kind of characters of old, and so I quite liked him because he had that steely look, and I thought he was a brilliant Batman. There's something different in the skies. Batman's access to the world's satellites are showing some unusual behaviour of a returning asteroid from the assumed location of Krypton. Whilst this poses no immediate danger of impact, using predictive models, the world's greatest detective has deduced that a chunk of the asteroid had broken off 200 million years ago and collided with the Earth. If Batman could work this out, then it won't be long until Lex Luthor does the same. The race is on to find it, but how? Great, so the race is on to find this chunk of asteroid, which is assumed to have some kryptonite in it. But how on earth could Batman go about trying to find this? I guess one of the kind of most immediate things that springs to mind is when a great big chunk of rock hits the Earth, it's going to leave a big dent and a big hole, isn't it? So what we'd want to do is try and find evidence of where it struck, and then we'd have to go out and do some hard graft and try and find that bit of kryptonite, I think. So yeah, we need to find some evidence of where that impact occurred. So if it was a sufficiently small asteroid, because this, to be of value, this could be the size of a football or something that came through. It doesn't need to be the giant stereotypical Hollywood asteroid that we're thinking of. Would something of that size, or even say slightly larger, leave that much evidence, or would it be possible over 200 million years for that evidence to be covered up by movement? Yeah, no, totally. So what I would think is, the bigger the asteroid, the more damage it's going to leave. But what's always remarkable, I think, about these kind of meteorite impact craters is that you get a very, very big hole for a relatively small piece of rock. So you could have something which is, kind of football size in length, and it would leave a hole several kilometres in diameter. So the evidence might be quite striking. I don't know what there's different. We call them scaling relationships as a way of measuring or predicting or trying to assume what the size of the meteorite was based on the diameter of the hole it left. So we'd have to kind of have an idea of how big we thought the chunk was, and also going to your point about whether it hit on the Earth's surface or beneath the water, that will affect which tool we use to try and find it, I think. So let's say it did land in the ocean. You say it would leave a hole, but I'm imagining things like the seabed and sediment moving around. Wouldn't that potentially be filled after 200 million years? Yep, totally. Yep, it would be filled in with younger sediment. Also, if the crust is subsiding, so the Earth's seabed or landscape surface is subsiding, you'll get sediment filling it in. So we'd have to have a way of remote sensing that crater if it was buried now.
So what exactly is sediment?
Go on a beach, scoop up a bit of sand, that's sediment. If a meteorite impact occurs, so a meteorite hits the seabed or hits the land, you'll smash those rocks up, obviously, because there's a huge amount of energy goes into the surface. So you'll have lots of those rocks are just catastrophically smashed into millions and millions of pieces of varying size, from big, house-sized chunks down to things you'd have to look under a microscope to see. So all of that sediment of those different sizes will all be shot up into the air or into the water column, and then they'll all kind of sediment back out. So they'll all rain back out of the water column and fill in the hole. So that's what would make it challenging. So there'll be what's useful for us is that there'll be some evidence that there was an impact, even if the thing is buried.
So has there been any real-world examples of asteroid impacts that have been discovered? Are people actively looking for these kind of things, or are these the kind of things that are discovered by accident?
I think a bit of both. I think there's probably, like there's kind of storm hunters. There's probably like meteorite impact hunters who go around in four-wheel drives in Arizona probably trying to find them. With things like Google Earth and remote sensing, we probably know where all of these, because they're so obvious, these big circles, and you can sort of go and see them. What is more challenging are ancient meteorite impact craters that are now deeply buried, and especially those that are deeply buried beneath the sea, beneath the oceans.
So what would be the process for trying to uncover one of these ancient impacts that are buried beneath the oceans?
Actually, most of the ones that are kind of offshore have been discovered by accident, really. If I'm to think of one which is very close to home, the Silver Pit impact crater, which is offshore the UK, offshore the eastern UK, out into the North Sea, that was discovered when seismic reflection data, so these X-rays of the Earth, were being collected for hydrocarbon exploration. So it was pure chance that this anomalous feature was discovered whilst doing something completely different.
So tell us about those X-rays, because that sounds like the kind of thing that Batman could use.
Yeah, it'd be a very useful tool because it allows you to see the unseen. So what we do is we have a source of energy, of like a source for sound waves. So we let off a big bang. So olden days, dynamite. In the seas now, you'd use something called an air gun, which releases a big bubble that effectively pops. Those sound waves go down into the earth and they reflect back from the different rock layers, and they come back up to near the boat or just behind the boat, and we record them with a series of sensors called seismometers. So we're listening to the sound which we released and listening for when it comes back to our sensors, and from that we build up this X-ray of the Earth.
Is that how an X-ray that I know and love from a hospital works? Is that based on sound waves as well, with different types of bone, muscle, etc., returning different things, or like?
Yeah, I think in the X-ray sense, as if we to really explore the analogy, in that case, it's to do with passing X-rays through something. So you or me, and that some of the energy is absorbed to varying degrees by the soft tissue and by the bones. So the seismic reflection method, so this type of data we might want to use to look for this meteorite, is different in that we're not really passing the energy through and recording it on the other side. We're actually passing it down and then getting a bounce and then picking some of it up back right near where we set off the source, really.
Is it better to think of it more from an abstract idea point of view in the same kind of way as like a sonar?
Yeah, that would make sense. I mean, there's different, the frequency content and what you're able to detect and the subtleties of the world around you that you're picking up are different, but the amount of what you're hearing coming back to you is dictated by the properties of the material. So depending on the rock types, you get different amounts of energy coming back. And we as geologists and as geophysicists, as earth scientists, we are trying to use that to understand what the different rock types are beneath our feet. So for the meteorite impact crater, we might be able to see evidence of those very, very broken rocks versus rocks which aren't so broken.
So I have this picture from textbooks of a child as a very neat and clean layered earth with different layers in it. But I'm assuming that's probably way more messy in reality. So how accurate a picture does this ping back? I mean, are the layers quite as neatly organised as I'm thinking, or?
No, the layers under our feet are typically very, very deformed. So they could be fractured, they could be folded, and the reason being is because of essentially plate tectonics. The Earth is, although it looks very passive and static while you're standing on it now, it's kind of always moving, and there's bits of plates pushing against each other or being pulled apart. And all of those structures related to those tectonic processes are down beneath our feet. And so this technique, what we often see across large parts of the world is that record of those previous Earth history events. So hundreds of millions of years of the plates moving, the structures associated with that, we can see them very clearly using these techniques to varying degrees. This technique is not perfect, and we can't see really, really small structures, but it can see some of the bigger structures that have been formed.
And the idea of plate tectonics itself is relatively new, is that correct?
Yes, it is. 50 years or so.
So it's actually younger than Batman.
It's younger than Batman. Yes, exactly.
Amazing. So what was the theory of things like mountain ranges, a connected land mass, etc.? Or was there even an idea of a connected land mass before plate tectonics came?
Yeah, I think people had looked at the rock record, as we call it. So they'd looked at rocks in different places, and they'd looked at fossils, so looked at evidence of life in different places, and from that deduced that bits of the Earth which are now not together previously were. So there was enough similarities there to deduce that there used to be land masses of various sizes stuck together. I guess the critical thing is that plate tectonics then provided a kind of physical explanation for the forces which drive the plates to move around and stretch in some places and to build mountains in other places.
Okay, so it was almost up in the air as to how these connected rocks and things were able to exist?
Yeah, there were different ideas out there about some processes with varying degrees of believability. And remember, historically, when religion had a stronger hand in science, there was a kind of much more a readier explanation for why these phenomena occurred. And so I think science was probably driven to come up with something which didn't involve a creator.
Right. Okay. Thank you. So to draw a conclusion, using these techniques of X-rays and analysis of crust, Batman, with a variety of different expeditionary teams, should hopefully be able to find evidence of this asteroid impact, and then it would be a case of drilling and extraction to save the day once more. So thank you very much for joining us today, Chris.
Thank you so much for having me on.
If you'd like to discuss your research on a future episode, email us at info@figshare.com.